Hi, welcome back to Online Statistics. As you know, I'm Naomi Lowe, and today we will be covering Lecture 5. This is about hypothesis testing with means of samples. So last week, we talked about how to perform hypothesis tests, but we used a score, just one single score, to test our hypothesis. That's not typically what we do, because what you know from one score doesn't tell you as much as you know from a handful of scores in a sample. So we're just applying what we learned last week to taking a mean and using that mean to perform a hypothesis test. So first we'll talk about the distribution of means. Remember, we were talking about the distribution of scores, the standard deviation of the scores, but now we're going to be looking at the spread or the distribution of means. If you took a mean over and over and over and over and over from a certain population that you're comparing, the null population, the population if the null was true, what would those means look like? So that you can compare not only your score, but now you can compare your mean to that distribution. This distribution of the means is also known as standard error, or standard error of the mean, SEM. Standard error can also be abbreviated SE. So anytime you see distribution of means, standard error of means, or our standard error sigma with a little m at the bottom, that's talking about standard error or distribution of the means. Next, we're going to talk about the process of hypothesis testing with means, so using the standard error to perform a hypothesis test where you compare sample mean to the mean of your population that you're comparing it to. Okay. And then finally, we'll talk about confidence intervals, which is a little bit of a new concept for you, but it's just related to your 95, 99% cutoff rates that leave the 5% or the 1% in the tail. It's creating an interval rather than just making a decision going on one side or the other of that cutoff. And then we'll learn how to create a confidence interval. All right, so first, the distribution that we're talking about today. Keep in mind, this is the distribution of means. So if you have a population and you took one mean from that population, so remember there's a population of kids playing video games, they take this math score. This population has a mean of 70 and a standard deviation of 2. If you take a score from that, that's what we had talked about before, but now a sample. Say you take a sample of 5 kids and you test them on this math test. You take their average, that's the mean. Then you take another sample of 5 and you take their average. Now, if you did this over and over and over and over and over and over and plotted those averages, what would the distribution of those averages look like? Now, you would expect to get most of those averages from your samples somewhere around the middle of your normal curve, because most of your data is there anyway. So most of your means are going to fall around that center of your normal curve. But then some of them might end up in the tails. Is it possible to get a kid from a population with a mean of 70 and a standard deviation of 2 with a score of 80? Sure, not likely, but possible. So you might end up getting one kid that's 80, one kid that's 70, and you end up with the average that's a little bit higher. So it's the distribution of, if you sampled over and over and over and over and over from this population at a certain sample size, a certain n, the spread of those sample means. Most of them would be in the center, fewer and fewer of those means would be further out. But the shape of this curve of the distribution of your sample means, if you took a lot of samples over and over and over, changes depending on how big your sample size is. So if you think about this, if you sampled 100 kids and you took the average of those 100, probably be pretty close to the population mean of 70. But if you took another 100, another 100, another 100, most of them are going to be close to that population average. But very few will be further away. So you're going to end up with this a normal curve that's not very spread out. Most of the scores around the center and a little bit on the edges. But if you only took a sample of 2 kids, you might just by chance, who you ended up with in that sample, get someone who was really poor at math. And so you end up with a really low mean. And then you might get a couple genius kids, really high means. If you're only taking 2 kids, if you take 100 kids, that's less likely to happen. And so with a sample size of 2, if you did this over and over and over and over and over, you're likely to have sample means that are more spread out because you get those extreme scores in both ends. Where a sample of 100, you might get an extreme score or 2, but you're still going to have those other 99 scores to bring the average down or bring the average up towards the center. So hopefully that's making sense. We're going to do a little activity to help illustrate what happens when you sample at different sample sizes. And then we'll take that distribution and use that to perform a hypothesis test using the means of the groups instead of the score. And so your comparison distribution now will be the distribution of all possible means, hypothetical typically, but we're going to actually create these distributions so you can see where we get our formula for this hypothetical spread of the sample means. Okay, so let's go to the drawing board. I have an activity that I want you to do. And for this activity, you're going to need 9 flashcards and something to write with. And probably a calculator. You can use Excel if you want to speed things up. This activity is going to take a little bit of time, but it's really important that you do this, and it's part of your homework. So you must do this. If you don't have flashcards, get pieces of paper. As long as you can shuffle them without a problem, then it'll work. So first you need to write 1, 2, 3, 4, 5, 6, 7, 8, and 9. Write one of those numbers on each of your flashcards. So I have here 1 through 9 on each of these flashcards, 9 flashcards. Then you are going to pretend that these 9 numbers are your population. So if you were just thinking about your population, this is what a histogram would look like of our population. Now remember, in real life, we never know what this population looks like, but today we do, because I want to give you an idea of what happens when you take samples from this population. So this is a histogram of it because we only have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and so on. Now, what you're going to do is you're going to take samples from this. So you're going to start off, first let's start off thinking about our population. Okay? Our population has an N of 9. It has an N of 9. There are 9 scores in our population. And it has a mean, remember this is a population mean, of 5. You can go ahead and calculate that. Add up 9 plus 8 plus 7 plus 6 plus 5 plus, add up these numbers, add up these numbers, and then divide by 9, and you'll end up getting 5. It also has a standard deviation of 2.58. Again, you could calculate that in Excel really quickly. Okay? So now we're going to look at what happens when we sample. You're going to take samples first of size 2, n equals 2. So you're only going to draw 2 cards from this population. So what I want you to do is practice random sampling. So you're going to shuffle these cards and not look at them so that it's random, and you pick out 2, 1, 2 randomly. I ended up with a 2 and a 4. Now you're going to record those scores. So you write down 2 and 4. And then you're going to do it again. Okay? So you're going to do this essentially 10 times. You'll do it again, take another sample. Random shuffle it. 1, 2. This time I got a 1 and a 6. You might want to put a line under your 6 and a line under your 9 so you know the difference. You record the scores. 1, 6. I suggest you have a larger paper so that you'll be able to record all 10 of these times you do this. So you're going to keep going, do this 10 times. After you've done this 10 times, you're going to calculate the mean of each of your samples. So this is one sample. That's sample 1. You're going to end up with 10 samples of 2. 10 samples of 2 each. So you add 4 plus 2 is 6, and then divide by 2 for your mean of those samples. So the mean of this first sample equals 3. Okay? Then 6 plus 1 divided by 2, and you get your second mean. So essentially, you're going to have a list of means. You're going to have a list of 10 different means from samples size of 2. Then what I want you to do with those means is make a frequency table like you've done before and a histogram, okay, with the different numbers. Now, thinking about this, could you, when you only have a sample of 2, end up with a 1 and a 2? And then what's your mean? 1.5. Could you end up with a 9 and a 10? Yeah. So you end up with a really low mean, 1.5. And could you get a 9 and a 10? Yeah. And then you end up with a mean of 9.5. So you might get a spread of scores that's pretty wide. So next, after you shuffle these cards and do the sample size of 2, you're going to move on and do a sample size of 5. Exact same thing, except for this time when you shuffle this, and if you want to work with a partner on this, that would be great. But shuffle, and you're going to randomly draw out 1, 2, 3, 4, 5. So now I have 5 scores. It's a sample of 5, a larger sample, which is typically better to estimate the population. You're going to record all of these scores. I suggest you open Excel, record the scores in Excel so that you can just click average and average these scores. You're going to need the average of these 5 scores. Then you're going to shuffle them, do it again. Draw 5, record the scores, record the mean. Essentially what you are going to want is the mean of all 10 samples at size 5 and of 5. You're going to look at those means. Now, you're going to do this again with the n of 8 10 times. So this can take a long time, but hopefully by the end of this activity, you'll understand why when you have a smaller sample, we have scores that are spread out more. At least not scores, means that are spread out more when you sample at a very small sample size. When you get to the larger n equals 8 and you record these scores, are you ever going to get a mean of 1.5 like we did with the 2 scores? No, because with 8 of these cards, you're going to have more of those numbers in there. Even if you get the 1 and the 2, which is what you got for your mean to equal 1.5, those aren't going to be alone. So you're also going to have 6 other higher numbers that draw the average up. So once you make these histograms, they're going to be different for each of you. You'll each do your own, and it'll be different for each of you. You might have, a histogram that's a little bit different for each of these, but you should get the idea that when the sample size is 2, it'll probably be more spread out, your histogram, than when the sample size is 5. It'll probably shrink a little bit. When your sample size is 8, it'll probably shrink even more. If we did a sample size of 9, the distribution or the spread, the histogram of those means of sampling over and over and over, and you're only doing it 10 times, so it probably won't be exactly perfect. But if you had done this, an infinite amount of times, this is where we get our sampling distribution of means. So here is an example of, you might end up with, once you do the n of 2 10 samples, you might end up with a distribution that looks something like this. A histogram, your little squares look something like this, and those all represent means. So graphing the means, you have mean, low, high, and you put the scores on here, and frequency on the y-axis, just like you did before. Your n equals 5 probably will have a distribution. It's a little bit less spread out. N equals 8. Now, and they should be centered around. Remember what your population mean is. So if your population mean equals 5, they'll probably be centered around that, because most of the time you get scores that give you a mean of 5, but every once in a while you get out further. With n of 5, they should still be centered around this 5. N of 8, they'll still be centered around that 5, but they'll be even closer. And if you were to go on n of 9, they would be even closer to that. And also, obviously, if you have 10, you've got n of 9 is the entire population, so there is going to be no variance. You have to, every time you sample, if you sample the entire population, you have the exact mean. So this is the spread or the distribution of means. And you see, as your sample size increases, as n increases, your sample size increases, the spread or the variance, the standard deviation, the spread of this distribution decreases. So as n goes up, the spread of the distribution shrinks. All right. Now, hopefully from that you gathered that there are some characteristics about the population that are similar to the distribution of means. So this mu with the mean under it represents the mean of all possible sample means at a particular sample size, a particular n. The mean of all the possible sample means, if you were to do it over and over and over, remember where all those samples were centered around? The mean of all those possible means, even if you get a high one, a low one, if you took all the samples of size 2 that you could get, the mean of all those means would be the mean of the population. Okay, so the mean of all the means is the mean of the population. Easy enough. Mean of means equals the same population mean. Now the spread, you saw that didn't stay the same. Okay, even though they're centered around the mu, the spread changes. It gets smaller as your n goes up. And so we have a formula that allows us to calculate how spread out the distribution or the spread of your sample mean. So if you had graphed all of those means, the histogram like you did before, and you calculated the standard deviation, not of scores, but of those means, it shrinks as n goes up. And so all you have to do to calculate the standard deviation or the variance of your sample means is you take the variance of the population and divide by n. Okay? So if you divide by a really large number, you divide your variance by a really large number, 1,000, that variance is going to be small. Okay? If you divide by a really small number, like n of 2, that variance is going to be larger, which makes sense because if your n is small, your variance of the means is large. If your n is huge, the variance of your means is very small, centered around the population mean. Okay? All you have to do for standard deviation of the means of the spread of means, of all possible sample means, is take the square root of that, of the standard deviation divided by n. So let's go to my drawing board. I have the same formula here, and you can see here is the means are equal. The standard deviation of the means equals the standard deviation by n, because as n goes up, it shrinks. The variance shrinks. The standard deviation is the same thing as the standard deviation of the means is the same thing as the standard error, or standard error of the mean, or distribution of the mean. So when we're talking about this distribution, we're talking about standard error of the mean, standard deviation of all possible means at this sample size. And since we just take the square root of this formula, and this formula is the variance of the population divided by n, then you can either do it like this, you take the square root of the variance divided by n, or you can simplify this and if you take the square root of variance, it's squared already, you take the square root, it becomes standard deviation and divided by the square root of n. So you can just, if you have the standard deviation, you divide by the square root of n, and that's your standard error, or your standard error of the mean. Now the shape, if you have a normal population that you're drawing a sample from, your shape should also be normal of your sample, or approximately normal. If you have a non-normal population, like the one we looked at that was uniform, if your sample is over 30, your sample size is over 30, then you should also have a normal distribution of the mean. This is because of central limit theorem. Suppose that you have a non-normal, so let's say that this distribution, and I'm going to put this up here where you can't see the top on purpose, but this distribution is skewed. Okay? Now, if you had a small sample, your small sample might also be skewed. But if you took a mean with a really large sample with 100 in it, you're probably going to get a mean that's close to the true mean of this population. And you're not going to end up out in this tail. You're going to be stuck here around this. And so your curve is going to look something like this. And this is the curve of the distribution of all possible means at a large sample size over 30. Okay, so central limit theorem is that the distribution of means will become normal. These means, even if the population is not normal, as long as your sample size is over 30. All right. So back to the lecture, I have a couple of examples here for you. A is a distribution of a population. Okay? It's a distribution of a population. And you can see it's a nice normal distribution. B is a sample that you drew from that population. And you can see this sample has a distribution that's approximately normal. Approximately normal. Now, our comparison distribution is represented by line C. This is the distribution of all possible sample means. Okay, so B is your entire sample, but if you just took the mean of that sample, it would fit into this distribution of all possible sample means if you were to sample, like you did in B, over and over and over and over and over and over and over a whole lot of times, an infinite amount of times, as many times as possible at that sample size, and plot the means, and your distribution looks like C. So C is a plot of means, B is a plot of scores in a sample drawn from the plot A, which has all of the scores in your population. So hopefully that's making sense, that we have these different distributions. We have the population distribution, sample distribution, and then we have distribution of sample means, or possible sample means. All right, so now that you've learned how to calculate standard error, or standard error of the mean, let's look at one way it's used in research. A lot of times, instead of giving you the standard errors away and doing significance tests, or even in addition to this, they'll list the means of different groups they're comparing, and then they'll just put the standard error bars on there. You see the little bars on these this bar graph. There are these little error bars that kind of look like a little confidence interval, like this. One of my stats friends, they had a birthday party for 1 year, and everyone wore hats made with these error bars. I thought it was kind of funny. So these error bars tell you what the standard error is, so that you know if it's a really large sample, these little errors should be small so that you know that the estimate of the population is good. If it's a really small sample, you know that if you have a small sample, you might, if the population mean is 5, you might get a sample mean of 1.5, a sample mean of 9.5. So you're going to be off. There's more error in your estimate of that population mean with a small sample size, and your error bar, your standard error, your calculation of standard error would be larger. So when you're looking and reading research articles, you want to note this bar and how close together or far apart it is. It's not good to have a large standard error bar. All right, so now the process of hypothesis testing using means instead of scores is just the same. You'll go through the exact same steps that you went through when you were hypothesis testing with one score. Now you're going to state your hypothesis, you're going to draw your comparison distribution, you're going to draw the cutoff score. And then instead of calculating a z-score from one score, you calculate a z-score from your mean, from your sample mean. Simple enough, you plot that z-score from your sample mean, and if it goes beyond your rejection region or your z-score cutoff, you reject the null. If not, you retain the null. So exactly the same, except your z is calculated a little different. The way you calculate z here is to take your sample mean, subtract the mean of all possible sample means, which is the same as your population mean, and then divide by standard error. Divide by standard error instead of standard deviation. So you remember that you used to calculate z with one score, taking the score minus the mean, and then dividing by standard deviation. Here it's essentially the same thing, but you're treating that mean as a score. So it's the mean instead of the score, the sample mean, and because you're using that to compare instead of a score, minus the distribution of all possible means, the population mean, divided by the standard error of the means, or the standard deviation of the means, which is standard error. So I have an example. Let's go back to our example from last week. This was the hypothesis that we had come up with for my son's video game, his little video game experiment. And let's say, remember the population had a mean of 70, a standard deviation of 2. We need to calculate standard error of the mean, or standard error. The way you do that is from a few slides ago. You should remember it's just the standard deviation of the population, 2, divided by the square root of n. And here n is 16. Square root of 16 is 4. 2 divided by 4 is your 0.5. Half or 0.5 is your standard error of the mean, or standard error, equals 0.5. Now, let's do the hypothesis test at an alpha level of 0.05. So if you recall, you look up in your z table, look up the 0.05 in the tail. It should give you a z cutoff score of 1.64. If you need to review that, go ahead and pause and do that. So if you go beyond this, you're going to reject, just like before. But now our z-score that we calculate, we're going to use a mean instead of a score to calculate this. So we take a sample. Here's our sample 1. And we have 10 students take this test. Instead of 1, this time it's a better test. We have 10 students do it. We take the average of those students who took this test. These students all played video games. Here's the average. We plugged in those 10 scores, took the average or the mean of these, and it was 67. So here's our population with a 70 in the middle. And so it's slightly below. Here's our sample mean is 67. So it's slightly below the 70. Remember, we're only going to reject when we're up there. So you already know that you're not going to reject. But let's go ahead and follow the process. You would change this 67 into a z-score. So you do that by taking your mean, 67, your sample mean, subtract the mean of all possible means, which you remember is the same as your population mean, 70, and divide by standard error, or the distribution of all possible sample means. So go ahead and do this. Let's bring the calculator in. 67 minus 70. You notice you have a negative number. That means your score fell below the mean. That's what happens with z-scores, or the sample mean fell below the population mean. And then divide by 0.5. We got a -6. So I drew this on here at the wrong place. It's -6 standard deviations. It's way down here. And so because we're only doing a one-tailed test, are you going to reject? Did it pass your cutoff? No. You don't reject the null, you retain the null. You decide that no, video games do not enhance your score on this test in math. Now, if we had done a two-tailed test at this -6, I'm guessing we would have passed the 0.025 cutoff, or the 2.5% cutoff there, but we didn't do a two-tailed test, so you just go, no, I retain the null. Same process as before. If you need to go back to last week's class and practice those steps, go ahead and do that, and then just plug in this Z formula for the mean instead of using a score. Simple enough. All right, so let's move on to confidence intervals. Now, confidence intervals are used with, it's similar to a two-tailed test. Instead of saying whether your sample score fell above or below, confidence intervals are used more to estimate the population mean. If you don't know the population mean and you want to estimate it based on your sample, we can take what we know from sampling error, or the distribution of all possible samples at a certain sample size, that formula I gave you before, standard deviation divided by the square root of n. We can take that and apply it to how far samples should be spread out and give a good estimate using the normal curve of where the population mean is. And so you just take the 99% cutoff or 95% cutoff that cuts off the outer 5% divided by 2 in those tails. So it would be 2.5 in one, 2.5 in the other. Or if you're doing a 99% confidence interval, you would take the outer 1% divided by the 2, so 0.5% in each tail. You take those cutoff levels in z-scores, convert them to raw scores, and that gives you your lower and upper limit of your confidence interval. So it gives you an estimate. You can either be 95% sure your population mean falls between these two numbers, or if you move it out a little to the 0.5% in the tails, you can be 99% confident that between those two raw scores, your population mean falls there, estimating it with a sample. So if you want to create a confidence interval, you need to first calculate standard error of the mean, which you know how to do. It's just standard deviation divided by the square root of n, or the square root of variance, which is standard deviation squared divided by n. So you take the square root of that too. You'll figure the raw scores from the 1.96 standard errors if you're out, above, and below the mean, if you're doing a 95% confidence interval, or if you're doing a 99% confidence interval, then you'll do a 2.57 plus or minus z score. So do you remember where those scores came from? Or maybe we didn't talk about it, but do you recognize those scores? If you were to look up in your table, your Z table in the back of your book, if you were to look up 2.5%, which is half of the 5%, the 95% gives 5% in the tails. The 2% is if you divide that 5% in 2, which you do with confidence intervals. So if you were to look up 2.5% in the tail, that would give you a 1.96 Z score. So that's the cutoff for that 5% tail. The 1.96, you convert that back to a raw score, gives you your lower and upper limit of your confidence interval. So let's go ahead and look at an example here. So here, this is using the information we just took. We had this mean of our one sample, kids playing video games, that was 67. It was way below the mean of kids not playing video games, the population we had compared it to. We also found that standard error was 0.5. We already calculated that. Now, we're asking, with a confidence interval, what is the mean of the population of kids playing video games? Population 1. What's an estimate? We don't know. We don't know what the mean score of kids' math scores would be from a population of kids playing video games. Okay, so we don't know this. We can estimate it based on our sample data. So we put our sample mean in the middle, and then we create a confidence interval around it. If we know the spread based on this 0.5 standard error, if we know the spread, so 0.5 is probably a little bit less spread out than that, we know that this normal curve, we'd have 67, and then we go up 1 standard error, it'd be 67.5, up 2 standard errors, and so it'd be 68, and 3 standard errors would be 68.9. So remember, if you go up 3 standard errors, down 3 standard errors, you're getting most of your data in there. So we're using what we know about this normal curve. We could take off 95%, which would be the z-score of 1.96. So it'd be almost to the second standard error up. and negative 1.96 and calculate the raw score using that 67 and the standard errors to correspond with those z-scores, and those we'd be 95% confident that our population score fell between those two limits of math scores from kids playing video games. Or we can move it out to this positive and negative 2.57 and be 99% sure that the population mean falls between these two cutoff scores. Now, you think, why not just be 100% confident? Because to be 100% confident, to get 100% under this curve, you would have to go in both directions indefinitely. So I could be 100% confident, but I would have to say I'm 100% confident that either direction indefinitely, that kids who play video games, on their math scores, their average is between 0 and infinity. Doesn't give you a whole lot of information. Yeah, I'm 100% confident, but it keeps going in both directions. So it doesn't tell me anything. You go, okay, that was a waste of my time. So the closer in I get, the more confident I get. I could say, we could cut off 68% confidence. In here, I can go, I'm 68% confident. It's, between these two scores, but they're very close together. And you go, oh, that's better that they're close together in what you think the population mean is, but 68% confidence isn't very great. So 95 and 99 are pretty much the agreed upon confidence levels. The way you make a confidence interval, you just take the mean, your sample mean. So your sample mean 67 plus z for your cutoff. So if you're doing a 95% confidence interval, you'll take plus 1.96 or your z-score times standard error times 0.5, and that gives you your upper limit. So let's go ahead and calculate that. We have 1.96 times 0.5 equals, so this is 0.98, and you add it to 67. So this here, if you add these together, is 67.98. And that's your upper limit of your confidence interval. So that's what goes right here, is 67.98. That's a raw score, the upper limit. And if you go down to the bottom of your 95% confidence interval, you do the opposite, 67 minus your z, minus z, which is 1.96, times standard error, 0.5. And so we already calculated that up there. All you do is 67 minus, and we multiply this, it's 0.98, equals 66.02. That's the lower limit of your confidence interval. That's this part that cuts off 95% under this curve. So you can be 95% confident that the average of the population of all kids who play video games is somewhere between 66.02 and 62 or 67.98. So that's a 95% confidence interval. If you wanted to go out 99%, you would just use the 2.57 in the z as the z for both of these instead of the 1.96. So hopefully that makes sense how to calculate a confidence interval. Just a summary of what we've covered today is that confidence intervals give additional information. So when you have, it gives you a prediction of what the population looks like, what the mean of the population is, instead of just telling you, yes, the two groups are equal, or no, the two groups aren't equal. It gives you an idea of, okay, if they're not equal, where does the new population fall? Or even if they are equal, where, what does it look like? So it tells you the confidence level. It also focuses attention on estimating the population, and it's less likely to be misused by researchers. Significance tests are necessary, though, using that cutoff on the confidence interval to make a decision whether to support your alternative hypothesis or not. It's a little bit dichotomous, as you see, if the cutoff, that 5%, sometimes might seem a little bit arbitrary. That's where the confidence intervals lets the reader see the information for themselves, but you still have to interpret it somehow. So the significance tests are important. Making decisions based on that's the best tool we have right now in making decisions on hypotheses. So hopefully this all made sense to you, and I will see you all again soon. Thank you.